This project was investigating manufacturing GDP and other factors influence the air quality and their impact on visitation. I'm Keely Lewis.
And I'm Arav Bajaj. So, for a point of interest, we are both interested in finding out how economic activity and different sorts of conditions in the environment, such as climate, region, and season, all play a role in shaping the air quality. We also want to look at and analyze whether these AQI trends from day to day and year to year have any influence over the visitation in parks across different states, national parks, monuments, and all of that. And then next is our purpose. So air quality is obviously something that affects human breathing and is something that's influenced by like a bunch of different things. And we want to see if AQI factors impact several different types of parks visitations and just find out what all can affect AQI as well.
So why we chose this topic and data sets going off of the purpose. So air quality affects millions of people and AQI provides a measurable indicator we could track at scale. Also, manufacturing GDP serves as a proxy for industrial output and a potential contributor to pollution. National park visitation data also offered behavioral insights into whether environmental quality changes people's decisions. So we expected to find that industrial heavy states leads to a worse AQI, and the worse AQI would then lead to fewer visitors. Also, seasonal and climate conditions would play a role in affecting the AQI as well.
So for phase one, this was our data collection process. Some of the sources we used was the EPA air data, Stats America, NPS for the API. This gives zip code, city, state, the classification. And then for the scraping, that was the manufacturing GDP by state to go back. And then we had the ZIP, the zip database. So this is the map to AQI to zip to park. And then this was originally going to be our HTML scraping. It was too complex. So we downloaded the CSV. That was for the annual visitation totals for each park.
For the data, just an overall the data collection process. So how we found them, there was lots of internet scavenging. We found the AQI and National Park API first, then public EPA, NPS, and Stats America portals. We then looked at the API requests. We did HTML scraping, and then we created an external CSV for the zip code alignment.
So for the data cleaning process for the HTML, this was really simple. All we had to do was abbreviate states. So obviously we parsed all the data, got all the states, and essentially we just wanted to abbreviate them. So as you can see on the left, Wisconsin turned into WI. I mean, turned into WI and WY, sorry. And then for the data cleaning process for the API, this gave us all the zip code, the address, the city, the state for the park. And this was more of a merger for the HTML, which would have been HTML and the downloaded data set. We essentially removed duplicate zip codes. We abbreviated the different national parks. We then put that into a dictionary. So for the park, it's not, it had the city, the state, the postcode. We made sure there was no duplicates in them. After abbreviating them, as you can see in the top right. And then finally, we also had to remove some of the zip codes that were had a value of zero or were only zero digits. And then later on, we ran into another problem where some of the zip codes had a dash at the end. So we limited it to zip codes with only 5 digits.
So for the downloaded data set, so we had two downloaded data sets. One was 2023, one was 2024. So essentially what we wanted to do was we wanted to separate the city and states. So in the CSV, the city and the state were in the same column, and we wanted to separate that into so it's a separate city and the state ID. And then if the city included the metro area, we wanted to split it by the dash and then only take the last part. So for example, if it was Atlanta dash Roswell, we wanted to take just Roswell to make it more specific. And then we wanted to merge the AQI data frame and then the zip codes to have it into one CSV. And then we dropped anything that didn't have a value and then converted the zip codes to an integer.
This was some extra data cleaning we had to do in phase three. Essentially, we had to explode some of the lists from the NPS API into clean rows. So we had to first accumulate all these different zips because some cities had multiple zips. And when we wanted to merge them, we wanted to make sure we can match to any of these zips. And that's why we exploded them. So that was for the matching. And then we also merged the AQI, the zip, the park name using multiple data sets. We also had to fix some of the park names that had inconsistent patterns with what we originally did. And then finally, there was a lot of duplicates with the cities and states, so we removed all of those. So for our Insight 1, what we found was that 57% of parks followed the expected AQI visitation pattern. So this is going to be a direct correlation between AQI and then visitation. So visitation increases, AQI increases, and vice versa. And then 40% did the opposite. So what we found was the correlation coefficient being negative zero point 0.1. This means there's essentially no relationship. That leads us to say AQI change is not a driver of year-to-year visitation changes. This is our code. As you can see, the right is the output, shows what we found on the previous slide. But just to run through the code really quick, we had to convert a lot of this to integers so we could perform the math. So we also did percent change, as you can see in the middle, and then subtracted the visitation for the change. And then we marked all these using helper function with either as expected or not as expected. And then finally, just to get the percentages, we accumulated the count, divided the total number of relations by the total count, and then got the percentages. This is our visualization. It's a scatter plot, and the green is as expected. Orange is not expected. No changes when there's 0% change in AQI. But as you can see from this, it's pretty obvious that there's essentially no relationship, and that backs up that correlation coefficient and tells us again that AQI is not going to be that main driver.
Now for the data insight two, which is the AQI differences across climate categories, what we found is that the warm state average is 52, moderate states is 49.8, and cold states is 48.4. So essentially this leads us to the conclusion that hotter climates can lead to slightly worse air quality, and this can be linked to density, wildfires, heat, and geography. And then this was the output of it. As you can see that the warmer states have the higher AQI. And then what we did was, or we wanted to group the AQI by the climate category and then created the average AQIs from that. And then so insight three, which was the manufacturing GDP versus average AQI. So we found that there was a mild positive correlation of 0.39. So more industrial states, I guess, tend to have worse AQI, but it's not that strong. And several low GDP states still have bad air quality, even though the industry is not the main driver. So this was the output of this code. So essentially what we wanted to do is I wanted to take the AQI data frame and convert it into numeric numbers. If there was any if they couldn't convert, then we ended up dropping that. And then I wanted to group the AQI by the state IDs, find the averages for those, as well as then create the different columns. And then I wanted to merge the GDP data frame with the AQI data frame. And then we wanted to find the correlation. Now, this was the visualization three. So we wanted to have two different y-axes, the blue representing the manufacturing GDP and the red representing the average AQI. So essentially for this, we had to use a completely different thing. We used the Plotly graph object or Plotly Go. So we first created the bar graph and then we created the scatter. And then so we used the secondary Y, and then for the bar graph, since it was our primary, secondary equals false. You can't kind of cut off, but for the red, since it is our secondary y-axis, secondary is true.
Then for insight four, this used the random forest regressor, and it was essentially saying or looking at how the seasonal AQI has its impact on visitation. So we found that fall and summer were the most important, and winter and spring were the least. And this showed us that seasonal AQI impacts visitation far more than annual averages. So this is our code. As you can see on the right, that's the output. And we essentially had to mark all these based on the month with their specific season. And we use our X independent variable as these different averages for the state for those specific seasons. The Y, what we're predicting was the 2023, was based on the 2023 visitation data. And at the bottom, you can see the feature importances. That tells us how much each one is important, how important each one is in predicting the visitation. This is our fifth and final insight, and this was the linear regression model. And essentially, this looked at the percent change in AQI plus the GDP and how that predicted visitation. So we had to remove some outliers, which we'll go into in depth in a little bit. But the R squared was 0.06. So that means AQI and GDP combined explain almost none of the variation in visitation. That also tells us that visitation has to be driven by some other unrelated factors, tourism shifts, marketing, weather, or events. And this is our code. The most significant part of this is just this was after our TA check-in. We had to remove some of the outliers to make our R squared just better. And it does lead to some inaccurate data to an extent, but it was necessary. But our x-axis was the percent change in AQI, and then also the manufacturing GDP. And then we were trying to predict the change in visitation.
Now for visualization three, which was the daily AQI across the US states. So there were seasonal shifts. So AQI levels do tend to rise during the summer and fall months due to heat, ozone formation, and wildfire activities. There are regional activities. So the Western states really show noticeable spikes during wildfire periods, while Southern states consistently report higher AQI across the year. There also is data or daily volatility, which you'll see in the animation in the next slide, and as well as geographic gradients. So northern and northeastern states generally have a lower daily AQI value throughout the year. So this is the visualization three. So essentially what we did was we created the choropleth map. And so how we got it to have the different frames is so we essentially each frame represents a day. So the CSV file had the average AQIs per day. And essentially what this was is this just represents each frame represents the average AQIs per day in the US per state. And the overall results and conclusions. So we kind of found that AQI isn't a meaningful predictor of visitation changes. The manufacturing GDP only mildly correlates with AQI. Climate categories explain more AQI differences than industrial output. Seasonal AQI matters a lot more than year over year AQI, as well as visitation is influenced by many different factors outside of the AQI.
And that is our presentation. Thank you.